The thing I love most about working in a machine shop is just how manual everything is. There are no computers figuring things out for me, so all the creations that come from these tools are a result of my own planning, focus, and coordination. The same could be said for this old drafting table. It is also a manual tool and is what engineers and draftsmen designed with up until about 30 years ago. By no means is it as fast or as efficient as modern CAD software, but like the machines, it takes a certain type of patience and a steady hand to create a beautiful, detailed drawing. So on occasion, I enjoy taking the time to draw out my designs. Actually, I have a project in mind that I need to do some design work on now. So join me as I take a step back a few decades and put together a design, the old-fashioned way. Now this project, what is it that I want to make? Well, I have this very nice 12-inch rotary table, and I also have a very small assortment of chucks for the lathe. So I figured why not combine the two and make a rotary chuck? Sure, this has been done before, usually by way of an adapter plate to connect the two, but of course I want to put my own twist on it. I'm going to mimic the D-type camlock mechanism that mounts these chucks to the nose of my lathe. If I do this right, I'll be able to quickly switch the chuck from the lathe to the mill and not have to break down a setup. Pretty neat, right? First things first, before I can start drawing, I need to get a whole bunch of measurements. A pretty deep search of the internet doesn't provide much beyond the few basic measurements for this D-type mount, so I'll have to reverse engineer the rest. The basic principle is that there are these matching tapers on both the nose and on the chuck that center and align the chuck axially. Then, a series of 6 cams pull the chuck tight against the nose, and in theory, prevent it from flying off here and crashing through my shop like a BattleBot. This might be a little easier to explain if I take one of these locking cams out of here. You can see the cam is mostly cylindrical, but with a scalloped area for the chuck peg to pass by. The region around the scallop is a bit smaller in diameter and also eccentric, meaning it's off-center from the larger diameter. So, as I rotate the cam, it locks into the corresponding scallop on the chuck peg. As I rotate more, the eccentric section begins to pull the peg and the chuck tighter and tighter until it's, well, tight. Now the details of this cam are the large portion of what I couldn't find online, so I'll get the rest of the measurements now. I'll be duplicating everything on here exactly, or at least within the limits of my tooling, so some non-critical features may look different. We already talked about the scallop and eccentric section, but there are a few other important features to note. This groove on the end gives a spot for the retaining screws to mount while also letting the cam spin freely. There's a hole in the bottom for a spring, which I can only assume is there to force the cams outward, so they don't rattle around like a bag of marbles when I don't have the chuck mounted. Lastly, there's a square drive hole on the end for a chuck wrench. And yes, I will be duplicating that square hole. Any guesses how I'll do that? I'll give you a hint. It will involve a not-so-little side project. The retaining screws should be pretty straightforward, looking like they're a standard 5/16 by 18 socket head cap screw with a pin feature turned on the end. Now for the more critical features of the nose itself. First, I'll verify the major dimensions of what I found online for the Type D nose like this, namely the outer diameter, flange thickness, peg hole diameters, and the hole circle diameter. While the info is pretty limited, I'm especially glad that the taper angle was included, because guess what it is? That's right, exactly 7 degrees, 7 minutes, and 30 seconds. Anyway, my best attempt with the dial protractor looks to give that angle as expected. The other important part of this taper is the diameter, or rather the major diameter here at the face of the chuck. This will need to be exactly 3.2505 inches, or else the chuck could end up either off-center or misaligned from the spindle axis. The only problem here is that the last little bit of taper is missing for me to measure, so I'll have to come up with something else. For all intents and purposes, I can use the shanks of these drills as gauge pins resting against the face of the nose and the taper. Then very carefully take a measurement outside to outside. A not so little bit of math later, and what do you know? Exactly 3.2505. I didn't expect that to work so well. Now for all the dimensions that weren't included online. Firstly is the position of the cam holes. As you can see, they're at an angle from the peg holes, but interfere with one another such that the cams grab the pegs like I demonstrated earlier. The real question is, what is this angle? I could try to cobble something together to measure this on the nose itself, but a much easier and probably more accurate way would be to measure the intended interference of the cams and pegs. Knowing the radii and the depth of the scallops on each part, I can sort out the intended distance between the axes. This would theoretically make up one leg of the right triangle formed by the spindle center, cam center, and peg center. The hypotenuse would just be the peg circle radius. Then a little arc sign magic tells me this is a 15.1 degree angle, which if I account for manufacturing and clearance tolerances, the true angle is probably 15 degrees even. Another important factor in ensuring that the cams engage properly is the distance of the cam holes from the face of the nose. I'll take the diameter of the holes and also the minimum distance on the front side to figure out where the center truly is. The retaining screw circle center is also probably going to be important to know since it ensures that the cams are held at the correct depth to work properly. The last thing I could measure is the center bore of the nose. This one is outfitted with a Morse Taper 5 mount that I typically use with my collet chuck adapter. I'm not sure I'm going to need this on the rotary table, so I'll just pencil it in for now. Alright, with all the measurements recorded, I can start drawing. Well, sort of. I still need to figure out how this will actually mount to the rotary table. The table face includes these 6 radial T-slots that seem like the obvious choice for mounting. So it might be a possibility that I can include some through holes in my adapter that intersect with these. But with so much going on here, I think it's best I make a preliminary drawing just to see if that will actually work. Even though I'm putting this together rather quickly, I'm taking care in making sure that everything is to scale, so this will actually be useful. You can see once I've added all the internal features, this part more closely resembles Swiss cheese. But I think I have just enough room for some counterbore holes in these open areas. There is one issue though. The closest I can get the T-nut hardware to the middle of the table is wider than the outside diameter of my chuck adapter. To make this work, I think I'll have to come up with some custom T-nuts with rounded ends that fit more closely into the slots. Since the counterbore holes I'll be adding to the chuck adapter are so close to the edge, I think I'll go ahead and make these counterbore slots instead. That will actually make it easier to install the hold down hardware anyway. That takes care of the mounting, but there's one more feature I'd like to add. When I mount this adapter, it's going to be important that it's centered on the table. I could indicate it in every time before I tighten the clamps, but that's more cumbersome than I would like. Instead, I'll use this precision ground ID on the table face as a locating reference. So I'll plan to include a very accurate diameter shoulder on the back side of the adapter plate to match. This only presents one small problem. In order to have enough material for a shoulder on the back, I have to give up the idea of including the Morse taper on the front. See, this is why it's a good idea to mock everything up before doing the final drawing. Get all that figuring and erasing out of the way so when it comes time to make it pretty, everything is clean. Speaking of which, I think I'm finally ready to do just that. With the addition of some mounting hardware, this project has had a little scope creep, but we'll just take it one sheet at a time. And of course it all starts with the border and title block. Nothing fancy needed here, just some fields for a description, date, scale, material, and of course a company logo. The first part I'll draw out will be the main body, and I have enough room here to make this a 1:1 scale. I'm thinking I'll need 3 views for this, a front view, a side view, and also a section view to help depict some of the internal details. I'll space these out evenly, leaving enough room for where I'm expecting most of the dimensions will need to be laid out. Now I'll start adding more of the details. For this front face, I have a lot of features at a lot of angles. Fortunately, I have options for how to draw these. Standard triangles work great for the common angles, but I also have the drafting machine itself that can be set to more obscure angles. This especially comes in handy for measuring distances at those angles, like I need to for the diameters of these cam holes. All of the internal hidden features need to be distinguished from the visible external features, and that's where the dashed lines come in. The center lines and center points are also distinguished even further by long dashed lines. These will be especially useful later when I add the dimensions. Then there's even another type of line with a double dash that depicts a section view cutting plane. I have this passing through 2 different angles to help depict the peg hole details separate from the cam hole details. I'll actually go ahead and draw out this section view now. Views like this are especially helpful when you need to depict some specific hidden details more clearly, like how these retaining screw holes intersect with the cam holes. The rest of the field that depicts solid material then gets filled with hatch marks that, as I only recently learned, correspond to specific materials. This one happens to be the general hatch style for steels like the 4140 I'll be making this from. The final view is the side view, which will be mostly used for depicting the diameters and angles of the locating features on the front and back. But the cam holes and mounting slots are also visible from this side as well. Since all these features are at different angles and therefore different widths, I can save myself a lot of math by simply projecting the different edges from the neighboring view. The holes end up being represented as ellipses, and there's some fancy math that can be done to perfectly represent these. But there are also stencils that will get me close enough for aesthetic purposes. I think that's just about everything. Last step is to add the dimensions. Now there are probably dozens of ways to dimension the different features, but I typically like to go with what will be the most helpful when I start machining. For instance, I'm planning to mill and drill all of the hole features while mounted to the rotary table. So if I were to lay out all the X and Y coordinates of the various holes, it wouldn't be very useful. Instead, I'll call out the centerline radius and angular locations of each hole. The rest of the dimensions follow the same methodology, referencing datums as I plan to indicate them on the machines. That about does it for the first part. Fortunately, it was the most complicated part by a long shot, so this next sheet should go a little quicker. The cams are next, and since I have so much room, I'll go ahead and make these larger at a 2:1 scale. Like before, I'll start with the general outline of each of the views, though this time around I think I'll need a few more than before. A view of the side, one of each end, and then 2 section views. The side view will show the details of the retaining screw groove and the peg scallop, while each of the end views will depict the spring hole and square drive. Now the section views are needed for some more of the less obvious features. Firstly are some of the hidden features of the square drive. There's actually a relief at the bottom of this hole. This is here to aid in the way the square drive hole is made. I guess now I have to spill the beans on how I'm actually going to make this. I'll be using a rotary broach. I don't have one quite yet, and therein lies a good side project. But we'll get to that in another video. Anyway, this relief gives somewhere for the chip to break off as the broach passes through. The other less obvious feature that needs a section view is the eccentric section in the middle. This is the mechanism that makes the cam a cam, but the cam will only work if the eccentric area is clocked at a specific angle. By that I mean, where within this larger circle does a smaller circle need to be? Inspecting the cam itself, the answer becomes more clear. The deepest part of the cam needs to line up with the leading edge of the scallop here. This makes sense given how this will be the first point of engagement with the peg scallop. So I'll draw this out to match and use a drafting machine scale to figure out approximately what that angle is. From here, it's the same process of filling in the dimensions based on how I plan to machine these features. With the exception of the scallop, this will mostly be a lathe project, making use of the collet chuck as well as the forejaw for the eccentric feature. I've got a little extra room here, so I'll also include a small detail view for the retaining screw with the pin feature turned on the end. One last and final sheet is for the custom T-nuts. The intent of these is to maximize how far into the table T-slot the T-nut will go. The slot itself was cut with a slot cutting mill, so it leaves a curved profile at the bottom. So I'll replicate this shape on one end of the new T-nuts to maximize the load distribution. These curved ends should be a fun little setup on the rotary table. Alright, that just about does it. That's all the details I'll need to machine these parts. Now I just need to get the material. I've got the big piece covered, but I'll have to order the rest and cross my fingers it arrives in time. I hope you enjoyed this little foray into some old style design work. I've actually had a lot of requests to see the drawings I've made for past projects. Excitingly, they're all available right now on my Patreon, where you can also enjoy early access to ad-free versions of all the videos. These drawings will be up there as well. But of course the drawings are just the beginning. Now I actually have to make this thing. As always, thanks for watching, and see you next time.